Hello everyone. So welcome back to CSE 112 Computer Organization Section 1. So today we will have our second lecture. So just for the sake of the students who could not join the first class, we will be updating everything on our Google Classroom platform. So please, if you have missed the first class, go back and check the lecture there. Myself Sujay Dev, and though we will be uploading the lectures, the recordings, but it's highly encouraged that you attend the live classes, because on the recording you will not get everything, especially the discussions etc. will not be included in the additional discussions. Sometimes some additional pointers will be discussed which will not be available in the recording. All right. So myself Sujay Dev, and I am associated with the AMS lab, Advanced Multi-Core Systems lab at IIIT Delhi, and we extensively work on in the domain of computer organization and architecture. So feel free to visit our lab web page, my Google Scholar profile, to know about our recent work in this domain. So today we will be talking about our or continuing our discussion on computer organization. So in the last lecture we talked about primarily the management part of the course, the logistics of the course, what will be covered etc. At the later part of the lecture, we also discussed about some motivating factors why we need to study about computer organization. So we will continue from there, and if we highlight the agenda for today. So the agenda for today will be as follows. So we will try to understand what is computer architecture, then from there we will try to see how computing devices have evolved over time and the kind of ubiquitous computing era we are living in. Followed by that, we will understand, or we will briefly talk about Moore's law, which largely is responsible for this exponential growth of computing devices in our life and the way they are penetrating in every aspect of our life. And finally, we will basically talk about architecture and the difference between architecture and organization. All right. So this is what we will be covering in our lecture today. And as always, feel free to stop me if you have any queries. So you can raise your hand or you can unmute yourself to ask your question. All right. So going forward, so we will try to understand what is computer architecture. Now before we answer that, as engineers, it's very important to understand the role of an engineer. So as engineers, our role is to purposefully use science to solve some practical problems. So which is very different compared to possibly a scientist, a physicist, because they are primarily focused towards exploring new phenomena of nature or new phenomena in that domain. But as engineers, we would like to utilize that phenomena or purposefully utilize that phenomena to solve some practical problems. So when we say that, then it essentially means that if we have some application in mind and we need to solve it, we have to ultimately use some phenomena which is available in nature to solve that problem. So we can think about different application. To start with, simple applications like if you want to navigate and you want to utilize a device to help you in the navigation process. So you can think of compass, right. So compass is utilizing a physical phenomena that magnets will always align with the magnetic pole of earth, and that is why it will always point towards north. So you can utilize this phenomena and you can build a navigating device. So here the application was building a navigating device and you use a physical phenomena. Now this is a very direct application, but you will not find this kind of direct application very easily. Some other applications can be we again use motors. Basically how we design motors, we have windings, and through those windings we pass current, and because of those passing current it creates a magnetic field which basically rotates, which forces the motor to rotate, and utilizing that you can build a fan, you can build maybe a car, basically car engine and so on, right. So everywhere we are using a physical phenomena or some phenomena related with our environment, learning from it, and we are purposefully using it to solve some application. Similarly, in our day to day life, the computers we use or the small gadgets we use, for example, let us say a calculator. So we need to do some big mathematical operations. For that we can easily use a calculator, but what goes on inside this calculator? So there is a chip, that calculator where the numbers are, when we press the numbers are translated into their binary form, and then the data is put into that chip. The chip contains lot of switches, thousands or tens of thousands of switches. Those switches synchronously work together to basically find out the exact answer and give us the answer back. So basically there also we are using physics or physical phenomena. How? We are using some switches which can switch very fast, and how we are designing those switches? We are designing those switches using some kind of semiconductor, at this point maybe silicon based semiconductors. So these switches are controlled by some passing some current. So basically you can control those switches, you can switch on or switch off those switches, and using these phenomena we are doing this calculation. So you see that whatever application we can think of is getting solved by some physical, by purposefully using some physical phenomena. Now if you think about it, this gap between the application and the physics is huge. Now if you are thinking of an application, let us say some image processing related application, and you want to find a solution for that. Now if you need to think about how that solution is actually getting translated at the physics level, then this will be a very overwhelming problem, because you will not be able to focus on only the application. You have to think about, oh, I have this algorithm now I have to run that algorithm on some machine which is built using some switches, built with transistors and all these things. Now if you think about the whole physics, basically how this application will run at the physics level, then for a single person or for even for a single institute, solving this problem will be very, very difficult. So what our computer architecture does, computer architecture at a very broad sense actually helps us in abstracting out or basically building some implementation layers in between application and the physical phenomena. So, this concept of abstraction is very, very important, especially in VLSI domain. So, one of the main reasons of VLSI being so successful or so basically it achieving so much growth, one of the primary reason is this concept of abstraction. So, what it says that you abstract out layer after layer and you focus on the abstraction layer which you are looking at. So, at a very broad sense, computer architecture helps us in building this different abstraction layer or implementation layer, so that we can implement our application in a very efficient way at the physical level. Okay. So, what are these abstraction layers? So, I have basically listed out all the abstraction layers, but that does not mean that all these abstraction layers constitute to computer architecture. So, just for completeness I have shown all the abstraction layers, and at a very loose sense we can claim that okay, from application to physics, computer architecture helps us in abstracting out all these different aspects. So, if you look at these different abstraction layers, so you have an application, and from that application you see that on this part, so you have your application. Now, the immediate abstraction level below application is your algorithm. So, you need to solve that, or you need to find out a solution for this application. So, you have to have an algorithm. Now, how this algorithm will be actually implemented in a form so that the machine can understand, for that you need some programming language, and then once you write it in the form of programming language, your operating system will figure out like how that set of instruction need to be communicated to the actual machine beneath it, so that it can be evaluated. Similarly, if we look from the bottom, so you have your physics, and using the phenomena of the physics you build devices in the form of transistors. So, basically you design let us say NMOS, PMOS transistors which are based on some silicon substrate, etc. Using those transistors you can build circuits, and using those circuits you can build gates. So, just to make sure we can recollect, these gates, circuits you have been exposed to in courses like digital circuits. Then you will be some of you who are in ECE. Okay, we do not have any ECE student here, but still in ECE we have a course called integrated electronics, where we talk about this circuits in more detail. There are several other courses which talk about these abstraction levels. So, basically wherever you deal with gates, circuits, so these are different abstraction layers. Similarly, in this you will find that okay, there are several courses in this application abstraction layer. You have ML, you might have some course on computational biology, you might have some course on human computer interaction. So, all these courses will come in this application abstraction layer. Then you have dedicated courses on algorithm, advanced algorithm design and so on, data structure and algorithm, programming language, maybe intro to programming, advanced programming. So, these are the Python related courses, etc. You have dedicated courses on operating system, compiler and so on. Now, you see that these different abstraction layer, one primarily these abstraction layers are very close to your applications, whereas these abstraction layers are more closer to the device, actual device, the physics related to it, etc. Now, in between them resides most interesting abstraction layers, which are instruction set architecture, microarchitecture. So, instruction set architecture, microarchitecture, they are broadly in the domain of computer architecture. Now, in this course of CO, we will be focusing on this microarchitecture. All right. So, the microarchitecture essentially tells us that how the instruction set architecture is actually implemented on the hardware. So, it is a bridge between instruction set architecture and the hardware. To some extent, register transfer level or RTL level is also part of this computer architecture abstraction layer, broad computer architecture abstraction layer. Now, there is a advanced course on computer architecture which will primarily focus on ISA, instruction set architecture, and how we can build more efficient computers, etc. So, that will be covered in the 500 level computer architecture course. Now, this is very, very important to understand these different layers of abstraction and where computer architecture actually sits. All right. Now, from this abstraction layer, layer diagram itself, you can guess that the instruction set architecture actually gives information to the programmer, which programmer need to know while writing the code, and I will come to that in more detail in our subsequent slides. So, this instruction set architecture is more like a theoretical aspect of how the compute platform will be, the theoretical information which the programmer needs to know. For example, whether he can use different addressing modes, how interrupts will be handled, what is the width of your or basically how many instructions can be executed at a time, and so on. Whereas, the microarchitecture is more closer to hardware, and it tells us how exactly the ISA is implemented on hardware. Here we will talk about pipeline depth. For example, an instruction will have several segments in it. Now, each of these segments will be parallelly executed. So, how many such segments should be there, what should be the width of your ALU, what should be the size of your or how many what should be the size, actual size of your physical memory, and all these things. So, these things will be covered in the microarchitecture part. All right. Any questions? All right. So, now let us see how these different abstraction layers actually influence each other. So, from the top you see that different kind of application requirements will arise. As we can see, as we progress, there are different needs of computing. For example, in the last class we talked about top 500 supercomputers. Now, why we are, or why everybody is so much interested into finding out what is the fastest supercomputer and so on, right? Because there is a huge incentive to reach to or to develop the fastest supercomputer in the world, because whichever country can achieve that, they will have huge strategic advantage, because they can make sure that they can put better encryption in their strategic communication, strategic data, so that nobody can steal that. On the other hand, like if somebody has the fastest computer, they can break the encryptions which some other countries might have. That is why all the leading or all the rich countries like US, China, they are racing towards achieving the exascale performance. So here the application requirement is driving the innovation. So the application requires that we really get very fast computers which can support maybe exascale performance. Now to achieve that, innovations are happening at different levels. People are coming up with better algorithms, better programming, ways of programming, parallel programming and so on. The OS is looking at what kind of optimization they can do, and that is pushing even the architecture to evolve, so that like we are talking about, instead of von Neumann architecture, which we will talk about, which traditionally the architecture we follow, can we think of something different, for example neuromorphic computing. So all these innovations are getting driven from the application point of view, because we want faster and faster computers, and the traditional computers may not be able to provide you the kind of performance you are looking for. So you try to propose innovations at each and every abstraction level, and they are kind of they can happen parallelly. So you do not have to really rely on the other abstraction level. So that is another beauty of this thing. Similarly, if you look at machine learning applications, so machine learning applications has lot of potential, and that is why we see that many solutions are proposing to use machine learning. So if we want to use, or you want to exploit machine learning, so you have to make sure that your architecture, your algorithm, your programming language, all are tweaked appropriately to support the machine learning kind of applications. And also the applications can be very attractive, and because these applications are very attractive, for example, let us say you say that okay, we will solve the problem of autonomous vehicles. Now when you come up with this application, then there is a potential of getting lot of funding to solve that problem. So basically many people will be interested in solving this problem of autonomous vehicles. Now so that once this application is there, now you can basically raise funds, and using that fund you can basically do research in all these abstraction domains, so that you can solve that problem. Now from the bottom abstraction layers, you do get lot of innovations. For example, the material science is helping us really shrinking the size of transistor. We can have more and more transistors in our chips because of the innovations at the material science level. It also puts constraints. For example, you can build transistors which has a channel length of 3 nanometer or even lower length, but then there are physical constraints which will possibly obstruct, or which will not allow the transistors to be shrinked further. So in those cases, so the technology will put constraints. So technology will also put constraints in terms of how fast you can switch a transistor, what is the maximum on current that you can support, and what will be the off current. So basically if you have let us say billions of transistors in a chip and all of them are having some leakage, because even if they are not switching, if they leak current, then the amount of current dissipation or basically power dissipation arising out of those transistors will be huge. So how do you tackle that? So all these technological constraints, and so what is the effect of having so so much high leakage current? Your if your application is battery operated, your battery will drain quickly and so on. So you see that this abstraction layers actually drive the architectural innovations. So applications drive or pushes the different abstraction level to achieve the required performance for that particular application. Technology puts constraints and it gives the physical limitations. Now in between, the architecture plays a very important role in giving feedback to both application as well as the technology, so that they can take the right research direction. All right. So the application requirements drive that, okay, what are the limits of let us say at architectural level what could be done, and similarly the constraints from technology which are coming, they provide that, okay, these are the constraints. So now in between, architecture provides the appropriate feedback so that both the application and the technology can find a middle ground to achieve the desired goal. So this is the contribution of architecture. So you see that it plays a significantly important role in any application you think of. All right. So I hope I could make this point adequately highlighted, and if you have any questions at this point, feel free to ask. All right. So going forward, let us very briefly look into the way the computers looked earlier. So this is one of the early computers developed by John von Neumann, who is also one of the pioneers in computer architecture, and it is named IS computer. And as you can see, the computer is of the size of a large room, and it has lot of switches, and those switches were implemented using vacuum tubes. So vacuum tubes, so this is pre-transistor era. So computer architecture were there before the invention of transistors. So these vacuum tubes were basically tubes with some control which can allow the tube to be switched on or switch off. So it's more or less like a valve, and there you had a control point through which you can switch on or switch off the cathode ray which passes through this valve. Now there were many such switches used in designing this computer, and as you can imagine, the programming that computer was really difficult. So programming means basically you have to physically connect some wires to get some mathematical manipulation or mathematical operations done using this computer. So, the programmability was very limited, the size as you can see, and but yeah, at that time it was one of the biggest breakthroughs, and because of those days only we do have the computers which we have today. But now moving forward, like this was in the around early 50s, 1950. Now, if you look at the computers which are all around us, you will see that the computers look very different. We have autonomous vehicles which have lot of computers in them, we have medical devices, we have home appliances, we have, you name it, almost everything has some computer in them, and they come in different sizes, different form factors, used in completely different applications, different environments, etc. So, how we basically could reach here from this point to this point. So, I will just switch off my camera. So, yeah. So, if you look at this, so the evolution is really very fascinating. Now, one of the reasons for this kind of evolution is of course the abstraction layer. So, as we discussed here, the application and the physics which is getting this application executed, or the purposeful use of the physical phenomena which allows us to run that application is divided into several abstraction layers. So, we have different abstraction layers for as we can see here, and this dividing this whole problem into smaller abstraction layers made this problem more manageable, or this challenge is more achievable, and that is why whoever wanted to build that solution, they looked at, okay, I need to build a let us say washing machine. So, what I will do, I will figure out the logic that okay, it will have this kind of functionalities. So, I will write down the algorithm that okay, if this switch is pressed, then the main motor will start running in this direction and it will run for this much time and so on. So, this algorithm was developed, then somebody wrote the program for it, and somebody then figure out that okay, like what should be the platform where this code should run and so on, and accordingly they will find out an appropriate chip that can be put into a washing machine which will work in this environment and so on. So, you see that each people are doing their job at their own abstraction level. For example, if I am I am designing the algorithm, I do not need to think about what chip I will have to use. Similarly, let us say whoever is designing the chip, he might not know that ultimately for what application this chip will be used, because he will be primarily making sure that the functionalities which this chip is supposed to execute are done appropriately. All right. So, this abstraction layer, dividing the whole problem or application into this different abstraction layer, helps us to achieve this goal. Now, to further emphasize this point, you will see that the way the computers have evolved, it is quite interesting. So, in the early, so we have seen that in the 50s, early 50s we had these vacuum tube based big computers which could do very limited stuff. Then the mainframe computers were introduced in the 60s. They were primarily used for data management applications, and they were primarily used in big institutions. So, several users will be using the same computer, they will have they will be using it in on time sharing basis and so on. Similarly, there were different computers like mini computer in the 70s, then the client server kind of IBM PCs were introduced in 80s. Then in the 90s we first saw the basically personal kind of computers which were mostly desktops, very few laptops, etc. And in 2000 we saw primarily laptops, then iPads, iPhones, we started using our smartphones, and by the time in this decade 1990 to 2000, in this decade basically the computer became a mass market product. Everybody had at least one computer in some form or other. Then in the 2010s the we could see more penetration of these compute devices in the form of wearable devices, in the form of IoTs, like we had so many different computers in different parts of our home. In our home appliances we had like Google Assist, voice command enabled, Amazon Echo, and so many other things. And currently we are in an era where it is said that there are at least 50 billion connected devices. So, that clearly says that we have multiple computing device per person, and this trend will continue and we will see more and more kind of these things. Now, how all these things was made possible? So, of course, architecture played a very important role, these abstraction layers played a very important role, and it was possible because if we look at the growth of number of transistors in our chips, that was phenomenal, and that is governed by, or that was predicted by somebody called Gordon Moore. So, he was one of the co-founders of Intel. So, in early in 70s he made a prediction, and the prediction was more like an economic prediction. It says that the cost per transistor will go will go down exponentially per year. So, he said that the cost of transistor will be half every 2 years. Now, people interpreted that prediction differently, and it also resulted in different corollaries, and ultimately the most popular one was that the number of transistors you can put in the same chip will double every 2 years to 18 months. So, depending on what kind of chip you are looking at, if you are looking at a memory chip, then it will double every 18 months. If it is a processor kind of thing, then the number of transistors will double every 2 years. Now, that prediction was very interesting, and the most interesting part of this prediction is that the prediction was holding true till very recently. So, you can think about the enormous growth the number of transistors had in our chips. So, just to visually explain that better, I am taking help of this illustration of Intel. So, Intel came up with their first processor, which was named Intel 4004 in early 70s. the number of transistors in that processor was around 2300 transistors. Now, if we equate one transistor with one person, then to accommodate that many people you need a large a music hall or concert hall kind of thing. Now, by the year Intel 286 was proposed in early 80s, it had 134,000 transistors. Now, the size of the chip was same. So, same sized Intel 4004 now has same size Intel 286, but the number of transistor is significantly higher. Now, if we go back to the same analogy of one transistor equal to one person, now to accommodate that many person you need a stadium, large stadium for that matter. Now, Intel Pentium 3 was proposed in early 2000 and it had 32 million transistors, and to accommodate that many people you need a city like Tokyo. And jump to 2011, you have Core i7 processors which has 1.3 billion transistors. Now, that is the population of China. So, now think about the situation like if we had the same kind of scaling applied as the transistor has scaled. Now, we are talking about the population of China being packed into a average size concert hall or a music hall. So, that is the growth. So, it is very hard to visualize, but that is what Moore's law has enabled. So, because of this phenomenal growth in number of transistors, the compute capabilities have gone significantly higher, and because of that we could achieve many of the innovations, and still now till now we are progressing towards achieving more and more innovation in this regard. All right. So, just to relate it with how it looks in a processor performance, with respect to processor performance, we see that this is a plot which is taken from one of the famous computer architecture book by Hennessy and Patterson. This is a logarithmic plot. So, here on the basically y axis, so I do not know where my pointer is. Okay. So, on the y axis, sorry about that. So, on the y axis you see that the performance is normalized with a very early computer which is called VEX processor, and the VEX 11780, and the performance of all the other processors are normalized with respect to that. So, I will just get rid of these things. So, you see that the way the compute the processor performance have improved is phenomenal. So, in a logarithmic plot, if you are seeing that the growth is almost linear, that means the growth is exponential. So, basically this plot is these dots are almost linear and it is a logarithmic scale. So, that means this growth has been exponential. So, you see that almost 52% growth in performance every year we could achieve for a long duration, which is phenomenal. Now, in this plot I will try to quickly cover three interesting points. So, in this plot you see that there are clearly 2 points which looks interesting. So, what happened during this what was the event that changed the performance in these 2 points? So, this is the point around 1985-86 where reduced instruction set computing was introduced. So, we will come to that in a bit. So, there are different kind of instruction set architecture, namely RISC, reduced instruction set architecture, and CISC, that is complex instruction set architecture. Now, as the name suggests, reduced instruction set architecture actually uses less number of instructions, and all the instructions are pretty much uniform. So, they will have same number of operands, they will take same amount of bits to be represented, and so on. So, reduced instruction set computing, because of its uniformity, you can design your hardware very efficiently, and that is why you see that the performance, there is a significant performance improvement once the RISC was introduced. CISC has its own advantages. For example, Intel's x86 is a CISC processor, whereas ARM etc. are RISC processors. CISC does not have this kind of uniform instruction format. So, in CISC you might have instructions which are, let us say, which have multiple operands compared to another instruction which does not have any operand, and so on. But in case of RISC you will not have this kind of a situation, it will be more or less uniform. So, that was introduced in 85, and that is why you could see there is a uniform, there is a sudden jump in performance, and then it continued for quite some time. Now, there is something more interesting happened here. So, everything was going fine, we were achieving more and more performance. Many of these performance gains were coming from architectural innovation, many of it was coming because of the device level innovation. So, please remember the abstraction level, the different abstraction layers. So, this kind of performance growth was happening because different abstraction layers were contributing at a different level. Primarily architecture was contributing a lot, and also the device level. So, there were more and more transistors to play with. So, the architecture architecture had more transistors at their disposal, and so on. So, that could be used for more and more performance. So, now this was going on very nice, but around 2000, early 2000, there was a serious problem, and that serious problem is famously known as basically power wall problem. So, again I do not see, okay, this problem is called, okay, sorry, I need to calibrate this pen, it looks like. So, this is power wall. So, what was happening? So, there are few things I think for completeness I should mention. So, the power consumed by a processor is directly proportional. So, let me just write it down. So, this is again I do not want to go into too much detail, but this is dynamic power. So, dynamic power is power consumed because of switching. This dynamic power is directly proportional to the frequency at which the processor is running, all right. So far you could see that the performance was, we were getting more and more performance because the processor was running at faster and faster frequency. So, if you closely look into these figures, you see that here the processor was running at some few megahertz, tens of megahertz, and then increasingly the processor is running faster and faster. Here we see that 500 megahertz, and then here we see that 1.3 gigahertz, 3.2 gigahertz, 2.6 gigahertz, 2.8 gigahertz, and so on. And I do not know whether possibly you guys will not remember, but there were Intel series processors which were coming, which were running at 4 gigahertz, and there were like many talks that okay, soon we will have much faster processors and so on, running at 6 gigahertz and so on. But then suddenly around 2000, early 2000, it was realized that we can't keep on increasing the frequency, clock frequency any further, because the amount of power the chip was consuming, and for that power to be dissipated properly, your normal cooling mechanism, which basically tries to force air on your processor to cool the processor, will not be enough. You need liquid cooling or even more sophisticated cooling strategies if you run your processor faster and faster, because you remember that you have put more and more transistor in a very compact area. So, and if you are dissipating lot of power, the power density becomes significantly higher, and there are some interesting anecdotes regarding that. Intel in one of their presentation actually at that time showcased that if this same strategy if we keep on applying, then by early 2010 or so, the chip will be as hot as our as the sun's surface. So, basically you can think of the amount of power density we are talking about. So, this problem was termed as power wall. So, basically there was a huge wall, we all were achieving more and more performance very easily, but then suddenly this huge wall came in front of us. So, we had to do something, and that is when the concept of multiprocessor or multi-core came in. So, what this concept says that this concept says that okay, you can't run the same processor at faster and higher and higher speed. So, what you can do, you can instead of one processor, you employ multiple processor and you run them at a moderate speed, and that is when the concept of multi-core came. And though the conceptually it looks very attractive and all, but and we should get almost similar performance, but because of other overheads, for example, the all the programs are not you cannot parallelize all the programs, you cannot share information very easily in a multi-core or for that matter moving data inside the chip is very expensive. So, interconnection network plays a very important role, and if you divide the same task into multiple processing engines, then you need to have coordination between them, you need to exchange lot of data between them, you need to maintain coherence and all these things, and because of all these overhead, the performance degraded a bit, and that is why we are no longer achieving 52% growth per year in terms of performance, but still we are achieving growth, which is also very healthy, 22% or so per year. But yeah, newer and newer challenges are coming up, and with the introduction of multi-core, the computer architecture domain became even more fascinating, because now you need to think of lot more other things. You need to think of how you share data, what are the shared resources your compute platform has in terms of interconnection network, in terms of memory and so on. Though we wanted to, so I think I have to stop here today, though we wanted to cover the difference between basically ISA, instruction set architecture, and microarchitecture today. Possibly we will cover that in the next class. So, just to quickly recap whatever, okay, so I will come to these things in the next class. So, just to recap what we have discussed today, we try to understand what is computer architecture. Basically we address this problem in a way of purposeful use of science, which engineers are supposed to do, and how this purposeful use of science can be achieved in a reasonable manner by abstracting out all the different layers between your application and the physics which lies between. So, computer architecture plays a very important role in that, and we looked at the abstraction layer, namely the computer architecture, which is very well coordinating between the application and the subsequent layers, and the device and or physics and the subsequent layers. Then we very briefly talked about the evolution of computer devices, how Moore's law played a very important role there. And in the next class we will talk about architecture versus organization. So, as always, I will encourage all of you to go through the book. The first chapter talks about it, the reference books also you can look at it. There are many other materials, and feel free to ask questions if you have any. All right. All right, thank you.